Hi everyone, welcome. We're going to get started in just a minute here. Welcome to the first part of Novinium's Smart Monitor webinar series. Today's topic is data collection for effective underground asset management. My name is Christy and I'll be your moderator for today's session. Before we begin, I would like to let you know that we encourage you to submit questions that you may have into the chat window at any time during the webinar, and we will address them during our question and answer session. If you would like to share the information presented today or go back to attend again, a recording will be available on our website after the webinar is over. I will now hand it over to Branko Horvat, Director of New Product Development at Novinium, to introduce our guest speakers.
Thank you, Chrissy. It is a pleasure and privilege to be part of this webinar discussion today. Today's webinar is set on the premise of the picture depicted as seen on the screen. Though comical in nature, this picture does have a serious side. We have this aging infrastructure that has taken on a life of its own. Public focus is on those items that can be easily seen, like bridges, roadways, pedestrian areas in our own neighborhoods. The net result is that the infrastructure below the surface, which is vital to our utility networks, is sometimes invisible. We react versus mitigate the issues, and sometimes is not well understood. How do we make this aspect of our business more visible so that we can mitigate versus react? So we have these underground electrical networks that become a critical part of the invisible infrastructure. We can't visibly see all that we want to know, and events occur because we lack data and signs of changing conditions. The problem, unfortunately, becomes very visible, as seen in the slide with smoking, fire, and the worst kind of event, explosions. However, by the time these events occur, we are containing the consequences versus mitigating the causes. How do we get ahead of the problem and be proactive versus reactive to the changing conditions underground? These events carry consequences that are of great size and or extent. There are 20 million manholes in the United States, which equates to about 16 people per manhole. We have greater than 2,000 events, and some indications have shown that we may be somewhere around 3,000 events or more in secondary manholes, which then lead to about or greater than 50 explosions per year. We don't see the number decreasing unless we put the right methods in place to mitigate the causes. So our first poll question is about the frequency of assessment. Our poll question is as such: what is the frequency of your infrastructure assessment program? Please choose one answer from the list of time suggestions below.
All right, I'll give everyone just a few seconds here to answer this question. And just a few more seconds. I see we still have some people voting, so I'll wait a little longer. All right, and I will be closing the poll.
So if we look at the Pareto of results here, a lot of you are saying every 5 to 10 years you're assessing your infrastructure, followed by one time a year from about 17%. As we go through this webinar today, keep in mind some of the things that HBK and Novinium are bringing to the picture here is how do we provide you that assessment of your underground infrastructure, not only understanding the underground infrastructure, but understanding it in real time. Keep this question in the back of your mind as we transport you through the very tools that can help you become more aware and be visible to your underground electrical networks. We want to connect this environment to the human beings so that we can make better and more economical decisions. How important is visibility in addressing your business problems? Please keep this question in the back of your mind as we move through this webinar. We want to start this journey with these key takeaways. We start with collection of viable data with a consistent, repeatable process, focusing on the capture of relevant, normalized information. Secondly, we want to use GIS-linked databases to house spatially accurate critical utility infrastructure characteristics and provide analysis capability. Thirdly, assessments of existing infrastructure that lead to the ability to plan corrective action, replacement, and remediation programs. And fourth, and the one that's probably most important, we want to mitigate risk by documenting and understanding your infrastructure's current state at any given point in time. We want to couple this risk mitigation with real-time remote monitoring, a predetermined set of environmental and infrastructure data to further mitigate risk and future asset failures. Without further delay, I'd like to introduce our main speakers from HBK Engineering. Mr. Don Kleyweg and Mr. Eric Bergstrom have over 20 years experience in the utility engineering industry, having dedicated the majority of their careers to design of underground power, gas, and communications infrastructure in dense urban environments. Their experience has ranged from the design and construction of high voltage underground transmission lines and complex power distribution systems to the development of technology-driven infrastructure inspection and mapping programs for large power, gas, and telecommunication providers. Their combined breadth of experience in the operational requirements and constraints for different utility types has allowed Don and Eric to provide unique insight to utilities planning and executing system refurbishments, upgrades, and asset management initiatives. We look forward to the conversation about how HBK Engineering services and solutions help us in understanding how we can better manage underground infrastructure issues. Welcome, Don and Eric.
Thank you, Bronco. So before we begin our discussion regarding underground infrastructure assessment, I'd like to provide an overview on HBK Engineering, our background, and our services. HBK Engineering is a full-service professional engineering firm with a major focus on utilities. Since our founding in 1998, we've spent our careers designing utilities, our main drive being on the development of safe, constructible, and efficient designs in very complex environments. We're headquartered in Chicago, Illinois, with offices in Pennsylvania, Maryland, Texas, and Iowa. Currently, we have over 400 personnel made up of professional civil, structural, and electrical engineers, professional land surveyors, inspectors, utility locators, and construction managers. Today, our clients include Exelon, including ComEd and PECO, American Electric Power, Wisconsin Energy Company, Pennsylvania Power and Light, American Transmission Company, Peoples Gas of Chicago, Nicor Gas, Verizon, AT&T, and Comcast. I do want to take a minute to talk also about safety. HBK has spent our careers working in trenches, manholes, and vaults, side by side with the contractors performing the construction of our designs. It's with this experience that we have taken the best practices from utilities and contractors alike to develop a safety program that is suitable for an engineering firm that has our hands-on approach. We recognize the many potential hazards present while working in underground power infrastructure, and we also understand that our greatest potential hazard is complacency through repetition. Some of the projects we're going to talk about now, we talk about tens of thousands of manholes, and when we looked at those from the beginning, we would say that the odds are against us to be able to perform incident-free. It's the complacency of repeating that same activity every time that we do an inspection that forces us to take steps to counteract that. We counter this particular hazard with experience and an evaluation of those potential hazards present at each individual structure, in which the crew discusses in a safety briefing prior to beginning their work. So with that, we have successfully performed over 40,000 power distribution manhole and vault inspections without incident. We attribute this to the experience and professionalism of our crews and our continued focus on safety. One of the programs that we want to talk today is where we shaped a lot of the ways that we process data, collect data in the underground environment, and transmit those results back to the utilities. In 2011, Illinois passed the Energy Infrastructure Modernization Act, also known as the Smart Grid Bill. As part of this legislation, Commonwealth Edison, the power provider for Northern Illinois, planned a program which involved the inspection and refurbishment of all of their distribution manholes and hundreds of miles of primary distribution cable. In the weeks after the bill was passed, HBK was asked by ComEd for a solution to the question, how do you inspect thousands of structures with multiple crews, getting information on hundreds of data points, and suggesting a course of action and making that data available to teams of planners across different offices the very next day? Over the next 15 minutes, we're going to discuss our approach to that problem and how we help solve it. Starting in January of 2012 and then ending in June of 2017, HBK had successfully inspected and assessed over 34,000 structures, capturing over 200 data points per manhole and over 60 data points per cable, in which there are 6 cables per manhole on average, with as many as 20 to 30 cables per manhole in Chicago's Central Business District. That translates to something on the order of 200,000 plus segments of cable that we're tracking information on at any given point in time. To boil our approach down to its simplest terms, we would put it like this. It is the physical inspection and assessment of a utility's underground system that is performed by a combined team of qualified electrical workers and professional engineers that is also augmented by real-time georeferenced reporting and work management tools. With this approach, we address a key number of considerations. We bring specialized system experience to the assessment with qualified electrical workers. Every system we've seen has had its own unique elements and concerns. So for example, if we are evaluating a lead joint, we would want a person who knows how to build that lead joint, making evaluations about its condition. The next consideration is that accessing each structure can take considerable effort, from traffic control setup to dewatering and potential full environmental cleanout. To maximize on the return of data for that investment of gaining access to that manhole, our engineer captures many other significant data points on the manhole outside of the electrical system. So during an assessment, our engineer will capture environmental data, structural data, and mechanical data, and make the most of that one single visit to limit the need for future visits for any repair work that is required. Our approach also takes the sheer amount of data into consideration and provides an overall framework for storing and housing those results. Over hundreds or thousands of structures, capturing consistent data is critical for making sense of the information, and it also yields greater returns in terms of valuable metrics that can be established by a utility's engineering teams and standards groups. So our first step in this process is identification of assessment criteria and critical system elements. This is the initial planning phase where we would go in and meet with the utility and really understand their major concerns, constraints, and issues. Usually occurring in the first weeks of any assessment program, the phase involves meeting with standards groups, engineering groups, reviewing existing plans and documents, and establishing a full understanding of the desired outcome of the program for the utility. During this phase, our team, working with the utility, develops a scope of the program and determines each data point of the assessment. It determines our planned reporting methodology, as well as the overall schedule, the permitting requirements, and other factors that can impact the work in the field. Some examples of this could be understanding things like the utility's cable racking methods or hardware specifications. Also, what they are planning in terms of restoration or remediation through that program. But it could also be something as specific as identification that there are terminations on riser poles adjacent to the manholes and that some of those could be deficient, which could also then represent a safety hazard within the structure itself. It's not evident from seeing that within the structure, but it's something that we would plan for in that initial state. The next step in the process is the development of our procedure and tools. And in this phase, we take the information gathered from the first step and we develop a full assessment procedure. Using the example of the deficient terminations on riser poles, we would now add the procedure of checking every riser pole that is adjacent to a manhole for those types of termination conditions prior to entering the structure. During this phase, we establish our crew configurations, our detailed work schedules, our permitting and environmental mitigation plans, as well as our data capture tools, our full assessment procedure, and our safe work plan for the program. One thing that we think has really helped shape the way that we capture our data and has really provided what we think is the most key element in consistent data capture is the customized data capture tools that we've built for these types of programs. Our data capture tools are designed to capture all the required data of any given inspection consistently and efficiently. Essentially, it will guide our crew from the first step of the assessment through to the end. It focuses on the data most relevant to the utility. In the ComEd program, we designed the capture tool to guide our crews from the initial steps that could be the safety setup for the manhole, in other words, checking the atmosphere within the manhole, but also then drill into something as specific as checking lead joint diameters to detect potential collapse or expansion of the joint components, which you can see on the right side of the screen. The same type of customization can apply to things such as grounding, secondary bus, switches, or transformers. Now, because the data is normalized across all the inspections, a utility has a much greater tool for analyzing the condition of their system and what contributes to those conditions. When evaluating, say, a specific cable jacket type across hundreds of thousands of cable segments inspected, a standards group can make some very good determinations about what factors are leading to the conditions that that type of cable finds itself in. And also, while underground power distribution systems have many commonalities, it is important to us that our assessments are custom focused to the utility and what is most relevant to their system. The assessment capture tool is designed with the end reporting in mind, provide the same key and relevant metrics across thousands of manholes from inspections performed at different times by different crews. The third step in our process is the physical field assessment. This process follows the assessment procedure and safe work plan developed in the earlier stages. Our aim with each visit is to capture or verify the maximum amount of information we can about that structure, its location, its position in the right-of-way, its condition, and the conditions of the elements within it. Our assessment crews are typically made up of 3 personnel: an engineer, an electrically qualified worker, and an entrance attendant. Each assessment follows the same basic procedure. The crew arrives on site, they evaluate the conditions external to the manhole, and they develop their safety brief. Once all crew members are signed off on that safety brief, traffic control and confined space equipment is set up, and the structure is prepared for entry. The atmosphere is monitored, gas levels are noted, and if those levels are compliant, then the electrically qualified worker performs a second safety check. That's a cursory visual inspection from the top for safety hazards that may be present within the manhole on the electrical system. If none are found, the crew will proceed with the full assessment. The electrically qualified worker will go in and perform his portion of the assessment, and then they'll trade up and our engineer will enter the manhole and perform the remainder of the assessment. With one full pass of the assessment data capture tool made, all the required data for the assessment has been captured. When that is complete, the engineer creates a sketch of the mapping of the cables with the manhole, the conduit occupancy, and then photos, digital imagery, other pieces of information are captured at that time. To get into some detail about the elements that we do capture during an assessment, we're trying to be as comprehensive as we possibly can with all elements. In the ComEd program, our assessments capture data pertaining to the electrical, mechanical, structural, and environmental aspects of each manhole. Each cable in the manhole was evaluated for a number of conditions: its jacket condition, its racking, joint conditions, leaks, exposed conductor. The grounding system was evaluated. If present, a secondary bus or secondary connections would be checked for blown limiters, fuses, which would be then noted for replacement. Transformers, switches, molded vacuum interrupters, and equipment such as that would also be checked, as well as any communications infrastructure and equipment, fiber optic cables, and slack coils. The hardware in the manhole is also inspected, and in this case, we treat it as a bill of material, listing the quantities of deficient materials for replacement. The assessments identified things such as deficient channels, brackets, missing saddles for cables or joints, missing sump covers, and pulling eyes. Additionally, the structural elements of each manhole are also covered. The material and condition of the entrance collar, the roof, the walls, the floor are noted. Environmental conditions are noted as well. Water levels, foreign fluids, debris, and vegetation are all captured. In many utilities, the non-electrical elements of the manhole inspection can sometimes not be in the mission-critical or desired criteria set for an inspection program. But we stress that for that time spent in setting up the structure for access, that capturing those data points The time involved is incremental and well worth the effort. A good example of this is to capture the typical water level. While we pump down each manhole prior to entry, the water will generally return to its level after a week or two. And that information can be extremely useful to a crew who may need quick access to the structure for future emergent work. With this approach, we feel that we capture the most complete picture of a manhole. The final step in our process is how we report. So at this point, we've collected this huge mass of information for each structure. How do we organize it? How do we store it? And how do we present it and make it sensible for users to look at it and mine through that to find the useful data they need to take the next steps? We know that in terms of schedules, getting 34,000 manholes containing over 6,200 feeders inspected and repaired in a 5-year window requires a momentous amount of planning, but it doesn't allow a lot of time to do it. So I want to go back to the problem posed to us as a question earlier. How do you inspect thousands of structures with multiple crews, get information on hundreds of data points, and suggest a course of action the very next day after the inspection? A large part of our solution was to leverage the data and the consistent nature of the data that we collected. If a set criteria was in place for what made certain elements deficient in terms of condition within a manhole, then it follows that we can use our database to take that data in, process the results, and instantly create a categorization or a roadmap for each manhole to follow in a workflow. So using a combination of web-based GIS tools and an in-house database, we procedurally generate the categorization for each manhole as it comes into the system. We place it into a workflow that starts it with simply, this manhole needs an assessment, and moves it to where it needs to go next. And hopefully ends with, this manhole either required no work or any work that was required has been completed. For instance, if a manhole had structural flags from the field, it would immediately flow into a category of structural review as pending. In that case, a licensed structural engineer would then be flagged to perform a desktop review of that manhole and grade it based on photos and notes from the field. They would either put it in two directions. One direction would be, this manhole requires no structural repairs and has remaining surface life on all of its structural elements, or it does require structural work, and then it moves into its next step in the workflow for structural work to be performed. The categories that we followed overall were the structural review pending and structural work needed, but then also into corrective maintenance only, minor cable issues, or major cable issues, which could indicate a cable that requires outage for major repairs or replacement. Repairs complete, or ideally no work needed. Finally, during each assessment, our crews capture a multitude of digital photos, 360-degree image that puts many people outside the crew right into the manhole. This is very good for looking at cable training, cable racking, how things are routed through the manhole. Our GIS data framework provides a very strong and user-friendly directory and navigation tool to retrieve these massive amounts of information as it's needed by engineering groups, by standard groups, by contractors, by in-house construction crews. And it makes the entire collection of asset information easy to migrate into the owner's internal systems as the assets are inspected and as programs are completed. To speak to further benefits about this level of data collection and leveraging this data to further improve asset data on a utility's behalf, I'm going to turn the discussion over to my colleague, Don Kleyweg.
Thank you, Eric, and hello, everyone. This is Don Kleyweg. As Eric alluded to, about 6 months into the manhole and cable assessment program, we determined that a large amount of potentially useful information was being collected during the process with respect to the underground electrical and physical infrastructure. We're also looking at our clients' current mapping depiction of their existing infrastructure, and we're noticing that these systems weren't up to date and accurate with respect to what actually existed in the real world. So we proposed to our client that we should further capitalize on the information that we are gathering and assimilating it into a complete update of the suburban GIS asset mapping and design system. After we worked through a few pilot programs with their team to demonstrate proof of concept, cost, and schedule, we discussed what was obtained as well as the level of effort required to move forward. As they began to understand the data being collected, they soon became further convinced that their new system designs and upgrades were being based on information that was 10, 20, and maybe over 30 years old. Subsequently, they agreed to move forward. we are able to take what was historically an electric connectivity model and convert it into a spatially accurate model. This also allowed for the team to include found equipment in and update the location of known equipment into the GIS model. For example, pieces of equipment could have been depicted on the wrong side of the street or in the middle of an intersection, leading to a misdesigned installation. The other important outcome of the design user standpoint was that we were not only creating the spatially correct depiction, but as a result of the data being collected, we were able to accurately depict position of a cable circuit within the cross-section of a duct bank. Prior to this, design users potentially perform a new design expansion to tie into a circuit that actually existed in a duct bank and manhole system on the other side of the street instead of in the location that was depicted in the GIS mapping system. Stemming out of the pilots, we proposed at ComEd what became known as their Underground Suburban Map Revitalization Program. This program included the underground infrastructure within ComEd's suburban service territory of over 11,000 square miles, including the verification and routing of over 4,000 circuit miles, locating and surveying over 1,000 miles of underground duct bank, and mapping and the integration of over 400 substations. The intent of the program is to make sure that our client ended up with an electrical model in their GIS mapping design system that accurately depicted their respective assets in a spatially correct model. Our team talked with various vested parties within ComEd, including their asset management team, their outside plant management groups, their system planning department, and their internal and external design groups, as well as their locating teams, to make sure that we demonstrated benefits to the groups. The benefits that were realized as resulting from the performance of this program are as follows: faster troubleshooting during outages, improved data for asset management, improved dig-in prevention and underground facility protection, identification of cables present for crews entering manholes, and improved visualization for the planning of system modifications and upgrades, and then ultimately an electric system model with spatially correct location of underground infrastructure. For example, from the design and planning point of view, they would now be able to make an efficient and informed decision regarding the ability to supply power to a new business. Another example would be in a large cable replacement program, the team would have data available to them to make decisions on which cables to remove and how to better plan outages with respect to impacted equipment and other circuits that could be involved. The locator company can now go out and perform their respective duties with a piece of information available to them depicting locations of underground infrastructure that they could more readily rely on as reference when they started out in the field locating cable systems, instead of the old version which could have been depicted the underground infrastructure as just a bunch of cables spread out across a 100-foot corridor or right-of-way. An underground installation maintenance crew could go look at the updated mapping system and manhole assessment information to understand where the cable system existed within the manhole, what ducts it occupied, and what else existed in the manhole. Prior to this, they had antiquated maps that may have inaccurately depicted 2 circuits in a duct and manhole system, when in reality there were 7 circuits going through the system. In short, this allows for everyone to better plan their work. From our engineering standpoint, as designers, the visualization aspect with spatially accurate locations allows for better design decisions when it comes to impacts to existing underground infrastructure, the public, installation hurdles, and things such as traffic control. As we looked at the approach that we were developing, we were going to take and tackle this program, the decision we made as a team to utilize the simplest and basic methods to data collection of underground infrastructure. This simple direct approach was to put locating and surveying crews in the field, accessing manholes and substations with the initial swipe at updated circuit maps to be toned, located, painted, and survey the paint marks of the underground infrastructure from the bus position at the substation all the way to the upfeed location on an overhead distribution pole or to the distribution cabinet or a piece of equipment where the circuit terminated. Thus, our crews would be surveying and near directly creating the spatially accurate maps of underground infrastructure based on the paint locates. Additionally, they'd be able to give the field crews that would use these maps in the future spatial references. We picked up visible references such as edge of pavement, the back of the sidewalk, nearest property lines, fence lines, in an effort to develop a nice base map for future crews to use in the field that has manhole locations with street outlines and names with relation to curb lines and sidewalks or duct bank alignment through a heavily trafficked intersection. What you ended up with is depicted in the snapshots below, with the left-hand side showing the system map as it was prior to the program, with cables just depicted electrically and no real spatial connection to any land base, whereas on the right-hand side shows the intermediate step that developed the map with the survey data of the locates and relevant reference points of land-based infrastructure. This is the final before and after of the program in the snapshots below, with the left-hand side showing the system map as it was prior to the program, as earlier stated, with cables depicted electrically, showing these cables strewn out through the corridor, shown without duct banks and no real spatial connection to any land-based. The right-hand side shows the final depiction of the underground system within duct banks, and now the cables are an actual asset mapped within the duct bank structure of the GIS mapping platform. The final slide for me is the tell of all why a utility would want to undertake a program to assess, update, spatially map, and accurately depict their respective underground infrastructure assets. The slide shows how the underground system map looked overlain on an aerial of the system. This is a 100-foot wide corridor showing the cables spread across the corridor. When actually they exist in a duct bank with a significantly smaller footprint. I believe that this slide helps to demonstrate why designers, planners, and even more so field operations individuals would value these updated maps as a great reference tool for use in all their work activities moving forward. We now have a poll question. What are your biggest concerns with your underground infrastructure? Please mark all as necessary.
All right, I'll give everyone a few seconds to answer this question. And just a few more seconds. We still have people voting, so I'll keep it open. Okay, I'll be closing the poll.
And with that, I now would like to thank you for your time and hand the reins over to Bronco, who's going to take you through how he sees this information we've collected in our programs to be the foundation in supporting system monitoring and maintenance moving into the future with this great snapshot in time. Bronco, it's all yours.
Thank you, Don and Eric, for taking us through the HPKey solution. You've shown that we can start understanding our aging infrastructure by proper assessments and documentation. I'd like to conclude our webinar with a brief on our next webinar, and we'll take some questions here at the end. In March 2017 of this year, we had a webinar called Causes, Consequences, and Protecting Your System from Manhole Events. Mark Newton, our VP of Engineering here at Novinium, took us on exploration of these manhole events we hear on the television and read in the news. In that webinar, we touched broadly on the manhole events, more from why they occur. On October 17th, we'll be conducting the second part of our Smart Monitor series webinars. In this webinar, we are going to explore the environment of manholes, associated events with these manholes, and more explicitly, prevention of these manhole events. As shown at the beginning of this webinar, we want to give you the tools that help proactively mitigate these events. These events are a combination of actions that occur in our underground electric infrastructure. The typical event is a combination of load changes in our cable networks that lead to cracking due to thermal cycling. When the coupling cracking with the conductive medium, which breaks down, in this case salt, down the cable further, but also provides an avenue for electrical tracking, or in this case arcing. While the cable is breaking down, various gases are formed within the conduits and open spaces underground in our electrical systems. The arcing combined with the gases lead to these events of smoking, fire, and explosions in varying degree. The costs are sometimes hard to measure, but exist regardless. Direct costs are the ones that are easiest to observe, since it's the very pieces of equipment and infrastructure we maintain every day. It's the indirect costs that can be very dramatic and extensive. We want to avoid those fines that are a result of events. We want to avoid the publicity that is a result of those events. And more importantly, we want to avoid disappointing our customers that rely on our service. In October, we are going to explore these events and how you can further mitigate the economic risks and costs. Think of this as going to Mars and trying to determine how we get there. What do we do once we get there? And how do we make the environment safe for us as humans to live near or in that environment? We'll be talking about the Novinium Prevent System solution. The system is made of basically 4 parts: venting of gases, water ingress control, smart monitoring, and finally communication of data to help facilitate decision making and further improve asset management. Our main focus of this webinar will be centered around active real-time smart monitoring of environmental underground networks. Smart monitoring of this environment is essential to addressing the underlying issues that lie beneath our cities and communities. Our webinar in October will take us deeper into how this data is displayed. Our web portal will give you deep insight to geographical understanding where issues may be starting and what trends might be emerging. Within each smart monitor, you will be able to look at distinct data relative to gases, temperatures, water level, and humidity. Imagine what you could do with data throughout your networks to prevent, mitigate, and remediate underground electrical networks. Imagine taking this data and mitigating the causes of failures in your network versus reacting to failures in your network. Please watch for an announcement on our second Smart Monitor series to learn how we can use this environmental to better understand your underground networks. In summary, and to conclude our webinar, data is essential to making good business decisions. At the end of the day, your customers will be satisfied because you are able to keep the networks healthy and providing that service your customers expect. Methodology leads to process, leads to consistency, which leads to great quality. We all need to make sure we are delivering the best quality our customers come to expect. And finally, understanding is the first step in good asset management. Because you took the steps to gather data and analyze it, you were able to mitigate those risks that were otherwise invisible. In our next monitor series, Smart Monitor series, we'll be looking at real-time assessments, which coupled with the HBK assessments of underground infrastructure provides you a wealth of information to further analyze your networks. I want to leave you with a quote that hangs in my office and I see every day when I'm thinking about solving problems for our customers and making our communities a better place to live. This quote comes from the American author named Alan Cohen, who writes motivational and inspirational books. The quote goes like this: "Don't wait until conditions are perfect to begin. Beginning makes conditions perfect." I hope you all start beginning today, and we look forward to having further discussions with you on this topic.
Thank you, gentlemen. Up here on the screen, you will see some additional resources, both about HBK engineering and Novinium's Prevent Manhole Event Prevention System. Again, this webinar will be recorded, so you can go back to retrieve this information at a later time. We look for an invitation soon for our next webinar in this series on October 17th, where we will go a little more in depth about smart monitoring and the developments that are being made to improve safety in manholes. At this time, we will move on to the question and answer portion. We have received some questions from our audience, so we'll begin to go through those. So the first one comes from Robert, and he asks, why are Novinium and HBK collaborating on this project?
We chose here at Novinium to work with HBK because we carry common vision, but maybe different methodologies of how we look at the underground infrastructure. I think coupled with HBK's approach to understanding underground infrastructure, our electrical networks, everything that they've described here today leads very well into our next Smart Monitor series, where we're going to actually take the Novinium Prevent solution, more specifically to smart monitoring, and we're going to give our customers a wealth of data, environmental data, which can be coupled with the assessments that HBK has done, and that will give you further insight to how you can improve your networks, remediation programs, and more asset management type discussions. At the end of the day, again, it's like we're trying to give our customers data so they can make smarter and better decisions.
Yeah, I'll add in on that from HBK's perspective that, while we think we've done a very good job in perfecting that one-time snapshot and how you can sweep through a manhole and figure out, all the conditions pertaining to electrical conditions or structural conditions, we naturally look at the next step of it being an active monitoring approach. And so we start to look at the work that Novinium does and how Novinium approaches the industry. We see that as a good next step in the evolution of assessing the condition and then continually monitoring the condition of that asset.
All right, thank you. Our next question is, do you feel it is important to do an HBK inspection or assessment before installing a smart monitor?
I do. I think that generally establishing baseline, and that first would be the establishment of a criteria of what actually represents deficient in terms of my assets, whether it be electrical or structural or mechanical, but then also going through and creating that baseline. In other words, so when you start monitoring on that, you're monitoring a known quantity as opposed to going into an environment where you've established no control at that point. I think by establishing your baseline data set and then monitoring, you have your starting point, and then you start to watch for your variations from that baseline. Which at that point puts more meaning into the information you're receiving back.
Yeah, to add what Eric just mentioned, I think they're complementary in nature. There's data from both sides. If somebody were to put in a Novinium Prevent smart monitoring system without the assessments, maybe they'll start seeing trends in environmental data, gas buildup, temperature changes, which then would lead to maybe, okay, now we need to go in and do further assessments. Again, on the other side too, the flip side, if HBK is doing assessments and they actually recognize areas of a network that maybe need to be investigated and looked at, that drives maybe that we need further data, which means smart monitoring real time will provide even a further level of information. You got to remember, smart monitoring is not only about being proactive about our infrastructure, but it's also to mitigate these manhole events that seem to be increasing in frequency throughout our country and becoming a nuisance to our utility networks, where they should be working on smart grid technology or building other types of electrical infrastructure, whether it's green or other types of electrical mechanisms out there. So I think they're both complementary each other. I think they not necessarily depend on each other, but they help further the information needed so that customers can make good, smart decisions.
All right, thank you. Our next question is, how do you access infrastructure between manholes that you can't see?
So we think our approach handles the first part of that question pretty well, which is when we go into the manholes and we perform our assessment, one of the key activities is of mapping the cables and understanding the duct occupancy. So if we understand what ducts are occupied by cables or bonding or fiber optics or tracer wire, we can then take those next steps to perform circuit verification, understand what circuits and feeders are moving through those. So now from two ends of that, say the manhole on either end of that duct, we understand what's in it. The next steps we could take could go as far as inducing a tone on either a conductor or a tracer wire that runs there and using RF locating to actually figure out its spatial location. But we still would not be able to tell anything about the condition of the cables in between those two duct entrances or the condition of the conduit package itself.
Some of the other things that we've been looking at with some of our other utility clients is they've asked us a similar question, and what we've done is we've proposed things like going out and simple rotting and proofing of ducts, and we've gone as far as utilizing smart pigs to be able to pull those through the existing ducts to make sure that there are clear paths for proposed and planned cable installation programs for the future.
I think the further that conversation is when we talk about here in Novinium and the smart monitoring between vaults, manholes, the conduits, it's an unseen environment. In a lot of ways, there could be things going on between those conduits that are creating temperature gradients, gas buildup. And so when we start talking in October with our next webinar series, we're going to get into more depth how you can use that data to further analyze your reliability of those conduit networks.
All right, thank you. Our next question comes from Abby, and she asks, did HBK do the underground electrical GIS mapping themselves, or did they provide the basic mapping information to the utility, and the utility mapped it themselves through their own GIS system?
Well, that question has two answers, depending on which utility. On ComEd, we supported that effort and helped them get back into their own system, which they called CGIS, ComEd GIS. Other utilities, we provided them with all of these shape files and all of the data associated with those respective shape files, and they imported it back into their own system because they had mapping resources that were available with GIS analysts. So we were able to do both ways. I hope that simply answers the question.
All right, thank you. Our next question comes from Travis, and he asks, what is the background of the engineer that inspects the manholes?
The background, pardon me, the background of the individuals that inspects those manholes are typically graduate engineers, field individuals that have spent, gosh, most of our guys average on 500 manhole assessments probably in their career to date. They all have electric hazard training, confined space training, quite a few other underground infrastructure accessing training that they go through certifications on a yearly basis. And they've all been trained on and through our process, not in just internal office, but also gone and spent time in the field shadowing other individuals in the industry that have gone through multiple assessments to date.
All right, thank you. Our next question comes from Joe, and he asks, do you foresee manhole events in the southern states becoming more prevalent?
Yeah, I think the answer is not simply stated, but I think geographically and topography-wise, there's differences between the north and the south. If we look at cities that are near coastal cities where there might be some salt ingress, where we get salt into the network systems, and it depends if they have secondary networks out there also. So I think it always depends, but there's always other reasons for putting in a smart monitoring system into a network. There's probably other environmental reasons other than what we typically go after in the secondary man networks. But I would say that it depends on which part of the country you're in. If you're near a coastal city, you might have more of these events that are occurring on. If you're inland, there are other reasons why you would want to be putting in a smart monitoring system.
Thanks, Bronco. Our next question comes from Jeff, and he asks, what are all the gases that Smart Monitor measured?
Yeah, so it depends on which part of the country we're in, but typically we measure the gases that cause issues like the fire, smoking, and basically the explosive events. Carbon monoxide was one of the main culprits that we watch. The other one would be methane, or CH4 is the other one. And in a lot of cases also where maybe we have organics that fall into a manhole, we might be watching for H2S. And then also are there any flammables that might occur inside a manhole. Depending on the customer needs, we have a lot of flexibility in the hardware, which we'll talk about in October, about how we can adapt to different types of sensors. Of course, the other gas that we measure all the time is oxygen, which is kind of maybe the baseline for how we make assessments on what happens in these manholes and these networks.
Thank you. We have one more question here, and it is, how long does it take to do a manhole inspection?
So the length of it can be driven by a number of factors, such as pump down time or setup time, but on average, over 40,000 manhole inspections, we've seen that 45 minutes seems to be a very good solid average for the time it takes to do a comprehensive assessment of each manhole.
Thank you so much, Don, Eric, and Bronco, for taking the time to speak with us today, and thanks to everyone for joining us. If we didn't get to any of your questions today, we'll make sure to reach out to you individually to make sure your question gets answered. Please take time to complete the survey at the end here, and we hope you enjoyed today's webinar. Thank you.